Right, good evening. It's good to see that some of you are still actually here, which is great, and have not gone to all the other talks that I wanted to go to, so I better make this interesting, all right? Did anybody go to Jimmy Bogart's talk earlier on? Yeah, okay, so did anybody go to Sam Newman's talk? Okay, for those of you, there's kind of a follow-on, and also Sam nicely managed to use one of the quotes that I'm using, but then forward referenced my talk, where I would talk, he anticipated correctly that I would talk about certain topics. Yeah, hello, my name's Kevlin Henney. You can find me kind of all over the place, if I can just get this, there we go. Given up keeping track of where I am. I am most active on Blue Sky and Mastodon for the short form. Occasionally I will do something on LinkedIn, but my blog is where other stuff happens if you want the really long form. And this is another introduction, really. So I will be referencing, I think I've got a Doctor Who, Hitchhiker's Guide to the Galaxy. There's a Star Trek reference, actually 2 Star Trek references. I'm missing a Star Wars reference, but there's no real kind of like time travel there, except for Rebels, but that's a different discussion. I was cruelly overlooked as one of the potential doctors, I feel, by the BBC. This is my audition. The fact that I was wearing a Space Invaders t-shirt at that moment was just brilliant. I hadn't really realized that until my wife had taken the photograph. If you are interested in recreating this experience for yourself, this is just outside. There's a cycle track between Bristol and Bath. It's a disused railway line. There's a cafe in Warmley, and this is right next to it. So for those of you who don't know, this is a TARDIS. It's from Doctor Who. For those of you that understand a little bit more about how things work, this is actually a toilet. It is actually listed as one of the most interesting toilets. There are books and listicles that list interesting toilets to go to. Yes, nothing is sacred on the internet. But I'm going to focus on the TARDIS experience. Now, does anybody know what TARDIS stands for? Correct. Well done. So, yeah, time, relative dimension in space. We will skip over what that might mean and just merely concentrate on the first and the last words, because that's what I want to talk about today. And one of the things, curiously enough, I'm known for is not being passed over as one of the potential generations of the Doctor, but error screens. People at me with error screens, and have done so for about a decade or more. I am known for failures. My name literally is associated with failure, which is a curious state of being. But here's one from a couple of years ago. Martin Fowler, observing Kevlin Henney, you ought to know that United may have discovered a kink in the time-space continuum over the Atlantic. Sadly, they weren't able to take advantage of it and get me home earlier. The kink being referred to as the time to destination, being 0. Distance, 2,600 kilometers. Now, that would be impressive if they could actually do that, time to destination. But let's take a step back here. Distance from Heathrow to Newark Airport, 100 kilometers. Well, let's put it into proper units. No, that's not centimeters. That's light. That's light milliseconds. 19 light milliseconds. So this is kind of a threshold. Just for clarification, because occasionally I get somebody trying to be pedantic. We're talking about the speed of light. When somebody says the speed of light, they mean the speed of light in a vacuum. They just don't put the words in a vacuum. That's how you can tell people with physics degrees, because they don't have to qualify it. Everybody just knows, okay? And that's what we're talking about. And it is very precisely defined. This is the speed of light in meters per second. In fact, to be precise, this is the definition of the meter. The curious thing is that if tomorrow the speed of light actually changed, it wouldn't have changed. That's a really curious, small piece of information that, you might think, wow, that's a really useful piece of trivia. However, if the speed of light changed tomorrow, the level of existential catastrophe that would visit the universe would be so great that you wouldn't be able to use that piece of trivia. We're developers, we'll just round it off, okay? Now, the thing about the speed of light, represented by c, is it is a constant. That's not why it's called C. It's called C because it's the Latin celeritas, which means fast or speed. I mean, I don't know what was wrong with just taking the Latin phrase for, oh, that's extremely fast and shortening it, but it is fast. Interesting enough, although we talk about it as the speed of light, light's just the carrier wave. What's really going on is this is the speed of causality. That's a very different way of looking at it. This is an evening talk for those of you watching online, so this is philosophically appropriate. It is best taken with a drink. Okay, so I'll just, if you hadn't come across this notion, this is the speed of causality. It's like, wow, that's kind of deep. So why does this matter? Well, because we're going to look at networks. And the whole thing that I want to cover, first of all, courtesy of the time machine, that is the ability to refer to past papers. This is a paper from 1978, Leslie Lamport. Time, clocks, and the ordering of events in a distributed system. You see, it's got a nice kind of slightly dry academic feel to the title, yet you also feel that it was deliberately chosen. He's saying something, and it's quite deep here. In a distributed system, it is sometimes impossible to say that one of two events occurred first. This is often a surprise to everyone, because we get used to the idea that time is something that we can perceive, and that obviously things are ordered in terms of events. And of course, on a computer, everything gets a timestamp, and we know how things happen. This is interesting because it's not a limitation in the sense of it's something that you can overcome. It's actually fundamental. It's wired into the nature of reality. And this comes as a hell of a shock to a lot of software developers because they're normally fleeing from reality to be software developers. And it's one of those points where the fiction that we call code actually hits the physical world. The relation happened before is therefore only a partial ordering of the events in the system. In this paper, this is kind of interesting because the idea of a happened before relation is actually very important from a threading point of view, and it has been used in tidying up the threading models of many languages, Java, C#, and C++. And I was involved in co-authoring a paper where this was an important relation to be able to say which of these two things happened before in the presence of multiple threads, and therefore what can the optimizer not do? It's a prevention on that. So understanding this relation is quite a deep one. And this is the paper it was introduced in. But it was also, from this point of view, it was introduced in the context of distributed systems as opposed to merely multi-threaded. And the observation, which seems prescient, this is the late 70s, okay? I would say I want you to cast your mind back to the late 70s, but I don't think some of you can. It's that far back. We found that problems often arise because people are not fully aware of this fact and its implications. I mean, this predates any widespread or any use of the internet that was noticeable. So this relation, A arrow B, means that it's possible for event A to causally affect event B. The idea that something happened here, and as a result, B is able to respond to it, use the information, or do something with it. So there is this. This definition will appear quite natural to the reader familiar with the invariant space-time formulation of special relativity. Okay, raise hands. Okay, there's a couple of you. Good, excellent. This is kind of interesting. I love the way he just casually tosses this in there. But what's quite cool is that he then goes ahead and uses this diagramming convention, which is actually a space-time diagram that is used to teach relativity. I was taught relativity at university, and this is a space-time diagram. And what he's trying to do is establish that people are in their own kind of local spaces. And although we're not necessarily getting the kind of deterministic effects that you would expect of objects moving at speed, the same reasoning applies. The idea is that there's a whole bunch of stuff happening, and your clock might be going slower than my clock might not even be set correctly, and we've got a difference of opinion over to the absolute ordering, but there are causally related events where I send something to you and you do something based on that. We can definitely say that those two things, there was a happened before. Everything else is a little less well-defined. So there is a whole idea here that he talks about creating a partial ordering and understanding this in a network. Now, this means that I really need to get to the point where I'm defining the terms and phrasing of this talk. So space-time is a noun. Sometimes it's written with a hyphen. It's basically Minkowski, in his interpretation of, timeline, 1905, Albert Einstein, who generally gets credited with far more quotes than he was responsible for, to refer to something in Sam's talk. But 1905, absolutely staggering year, 4 major papers, completely redefined modern physics. But interesting is many of the interpretations that came after. And Hermann Minkowski, 1908, thereabouts, kind of came up with this formulation. Wait a minute, if we just kind of take the axes on a graph and mix the 3D with the extra time dimension, then boom, you've got a thing. And it's a 4-dimensional thing, which is definitely hard to envisage. But the whole idea, we end up with this kind of concept of the space-time continuum, which I was about to fall off there. Useful in visualizing and understanding relativistic effects, such as how different observers perceive where and when events occur. Now, this is interesting, because that's exactly what we have in a distributed system. We might not have all the velocity craziness, but we do have the idea of your machine might be having a different perspective and perception of what's going on in terms of sequencing of events and times than my machine. But we still have to establish something. Adventures. What does this word mean? An unusual, exciting, and daring experience. Yes, that's what you are in for in this talk. Excitement arising from such experiences. Yes, that is exactly this talk. The encountering of risks. I will try not to, apart from falling off the stage, I will try not to do too much of that. A hazardous or perilous enterprise or performance. Oh, we're now in safe territory, because everybody knows about this. Okay? So let me go back to Martin. Published this book many years ago, a couple of decades back, Patterns of Enterprise Application Architecture. And one of the patterns he described was actually the Lamport clock, named for Leslie Lamport. This is effectively what he established in this paper. And summarized, used logical timestamps as a version for a value to allow ordering of values across servers. What is interesting here is that what you're doing is you're establishing a logical clock, a logical timeline that partially orders events. And there's an elegance to the basic algorithm, which I think is worth keeping in mind, because sometimes people do fall back on, oh, we'll keep the timestamp, but there's nothing wrong with keeping timestamps. Absolutely nothing wrong with keeping timestamps if you don't want to use them for ordering. If you want to use stuff for ordering across multiple machines, you need something else, or a lot of faith in the nature of reality. That, sadly, reality has been disappointing recently. So I'm going to go with use something like this. So if I've got the idea of send happens before receive, that's our fundamental idea. A send happens before a receive. Then the sender, what they do, the way we establish this consensus, and it's a consensus approach. This is what is so elegant about this. I think the first time I was ever taught this, I know I didn't appreciate the elegance of it. What we're going to do is we're going to keep a number. Let's just pretend it never overflows, okay? That's a separate talk. It's my failures talk. What we're going to do is I'm going to keep a counter. We're going to just say, oh yeah, when I start up, it's going to be 0. That feels like a good starting value. That's local time. Every time I'm about to do something that I recognize as an event, like a send to somebody else, I'm going to increment it. And I'm going to send my message, and I'm going to say, hey, this is my local time. And then the receiver will receive it. And they will do so without judgment. This is important, because they're not going to go, you call that a local time? No, they're just going to take that as an integer value. And what they will do is they will take that, and they will basically say, well, there's my time and the local time. My local time is now the maximum of these two plus 1. We just moved time forward. And this is how you end up with this ever-ascending scale. Now, that basically means that we can agree on an awful lot of things. There's a bunch of stuff we can't agree on, my local events compared to your local events. But with respect to the two of us, absolutely, this happened before that one. And so we've got this consensus distributed approach. It's surprisingly elegant and surprisingly simple. That's what I love about it. And we can find these kinds of things we have these things kicking around in various protocols for establishing and synchronizing time. And there's a whole lot of stuff, network time. I'm not going to get into that. So let's talk about the fact that most of us are working in one way or another with distributed systems. And right at the bottom we have IP. Most commonly we think about it as TCP/IP. Layered above that, HTTP. And then we might go higher with that, or that. We might worry about this kind of thing, and we've managed to evolve so far of the RPC of the 1980s, Feels like such a retro technology. Look how far we've come. Oh, gee. And we've got that, and it's just like surprisingly little. For those of you for whom, you know, the 1980s was also a long time ago, it's just like, oh, yeah, progress. We've gone from a world of services to making them microservices. Except the funny thing is, most of these, when they were created, were smaller than these. So this is a different reality. It's bigger on the inside or outside, or something's going on here, and I'm not sure what it is. But I'm not here to talk about that. That's the other talks. I want to talk about the theory that goes behind it. I'm not naming products here, because it's this idea that I want to understand the nature of distributed systems. So a number of years ago, I got my name on, I was involved in writing a book, Pattern Language for Distributed Computing. We gave a definition of a distributed system. A distributed system is a computing system in which a number of components cooperating over a network. So we have that. Leslie Lamport, at the beginning of that very paper I mentioned, a distributed system consists of a collection of distinct processes which are spatially separated and which communicate with one another by exchanging messages. Again, I'd like to remind you, this is 1978. However, the one that most people know Leslie Lamport for is this definition, which somehow feels more relatable. A distributed system is one in which the failure of a computer you didn't even know existed can render your own computer unusable. It's just like, that's the one I'm going for. That's absolutely the definition. So there's a couple of things I want to get to in this talk. So first of all, a CAP theorem. Who's heard of CAP theorem? Okay, so that's a reasonable number of hands, but not everybody. Fallacies of distributed computing. Yep, fewer hands. A note on distributed computing. Fewer still. Answer. Okay, yeah, that's exactly the ordering I expected. I'm relieved at that, actually. So, answer. This is kind of an interesting thing. This is a minor historical note. ANSWER stands for Advanced Network Systems Architecture. I mean, you've got to think, this is one of those ones where people sit and they go like, okay, before we do the project, what's it going to be called? Now, this was actually funded, this is a 1980s thing. This was funded as part of the ALVI program in the UK, which is all wrapped up in this idea of fifth-generation computing and all the rest of it, which is incredibly popular as an idea that died in the 1980s. What is also fascinating about the ALVI program is it demonstrates what happens when you're not in a position to circulate your literature worldwide. Because I was taught based on this. I was taught distributed systems. I did a master's degree in the early 90s, and everything, half of it, came out of this. Everything was in the shadow of this. And I thought, God, everybody knows this. No, they don't. It turns out not at all. So a lot of hey, sexy logo or what, right? Yeah, I said the 1980s. Okay, so here we have an engineer's introduction to the architecture, 1989. System designer's introduction, 91. For reference, I'm just trying to think when the hell I did my master's degree. It was during this, yeah. And there's some really interesting stuff, because one of the points that was made, we were taught very much, when you're dealing with distributed systems, and specifically I was there to study parallel computer systems, and when you're dealing with this, there are a number of things, what became known in the course as negative assertions. It is important, therefore, to identify explicitly the assumptions which are made for non-distributed systems and to ensure that they are absent from the models for distributed systems. To be precise, assumptions to be avoided. In other words, here are a number of things that are not true that you might assume. An important thing about assumptions is that they're normally invisible. And this is the interesting thing, is that although we are steeped in networks these days, you just pick up your phone, there you go. You're already dealing with a client in a network system. Although this is the normal state of being, we still default to a simple programming model and a simple computational model. Okay? It's just in our nature. There's nothing unique to software developers. It's not a matter of ignorance. It is simply a matter of the way that we like to understand the world, but also the way in which we are encouraged to look at the world. You're sitting there with your editor, and that's it. You get this beautiful sequential flow. Your programming language is designed to encourage you to think like that. Programming languages are incredibly bad at representing concepts that are asynchronous to them. They do not look asynchronous. If you want to understand concurrency, asynchrony, and things like that, Look at music notation. That shows you parallelism. Code does not look like that. Yeah? It shows you logical relationships, but mostly they are time-ordered. They do not show concurrency. There are only a few exceptions. In most languages, I mean, some languages have no opinion on threading whatsoever. I mean, JavaScript has no opinion on anything, including correctness, elegance, or anything like that, for example. And it doesn't do threading. But a lot of languages they have a strong bias away from that. But even when they do accommodate the idea that other things might be going on at the same time, they don't look like that. You know, most languages, you launch a thread by using a library. Look at the code. It looks like a library usage. It doesn't look like a thing that is happening simultaneously with another thing. Visually, it doesn't work like that. You are encouraged through your tooling to view everything from a particular point of view. But that just reinforces your assumptions. And mostly your assumptions are things you don't know that you're actually thinking. Mostly you discover your assumptions by accidentally stepping on them, like a Lego brick with bare feet. Ow. So let's look at these. Single global namespace. You cannot guarantee that everything can be referenced uniquely using certain names. You cannot guarantee that you have global shared memory. We get used to sharing everything, and it's just like, well, there's a thing over there. Oh, I want to share this data with them. Well, how am I going to do that? Well, you're going to have to send it in a message. And then we do discover that if you do try and share them in memory for any construct that allows you to do that, and there are ways around that, you then end up with other issues. Global consistency. The idea that everything is as you expect it, it's all consistently arranged and ordered. What you perceive is what I perceive, wherever we are in the system. Sequential execution. Things happen in a well-defined order. Leslie Lamport's already abused us of that. Total failure. Now, what do we mean by total failure? Total failure is the assumption that when something crashes, that's it. You don't have to worry about it, except for poring over the logs and all the rest of it. The point is, I don't need to do anything. If my program is self-contained and running in a single process, total failure means that process no longer exists. I no longer need to worry about it because I am not there. It's a very simple existential thing. The problem is that in a distributed system, I'm still running, you're crashed. We have partial failure. Partial failure is normal. Total failure is unusual. At that point, if you do get total failure in a distributed system, it normally means that the next world war has begun. Okay? That's a bad thing. Synchronous interaction. I call you, I wait, and you communicate back. Whenever we try and fake this up, the main effect it has is it slows everything down. It turns out that synchrony is a very simple way to reason. The protocol is called the stack. Okay? I call, in fact, that's a very good way. You might want to reframe the way you think about your ordinary function calls. One function calls another. What's actually going on? Call function is suspending until we get a result back. Okay? But synchrony also makes things really easy to reason about. It's just not normal, and it's a terrible waste of resources in a distributed environment. You've got inherently concurrent hardware, highly parallel. Locality of interaction. Yeah, most of it's non-local. Remoteness, you cannot assume this stuff. Fixed location, things move around. There's migration. Things also means you cannot direct bind to things and assume that you're binding to something in terms of I've got a connection to that or its name is not necessarily stable. And that everybody's running the same gear, the same version, the same everything. It's just like, yeah. And this is really interesting because what we've got here is a set of 10 negative assertions. Here are things you cannot assume. And most people stumble across these without realizing that they do so. Sequential execution being one of the kind of classic ones. Our languages support this view, but also inherently as human beings, we tend to think like this. You've just got to get used to this is the normal. Okay, that's the way things happen. Anything we do outside of that is to fake up the feeling of sequence, the feeling of synchrony. Okay, it's why classic RPC models, although they are easy to reason about, are also generally discouraged because they slow things down. Unfortunately, programming with asynchrony can be a little more challenging. You've introduced a whole load of extra stuff you have to worry about you never had to worry about. It makes things more complex. So the whole point here is everything just becomes more complex. Total failure. Partial failure, well, yeah, something's running, but something else isn't. So this is my publisher, O'Reilly, for books I edited, 97 Things Every Programmer Should Know. Fire in California, can't read your ebook in Pennsylvania. Well, this is awkward. The point there is that you've got this kind of awkwardness that something over there, a computer you didn't even know existed, is now preventing you from doing something. So we cannot get complete location transparency. Now, while we're here, let's deal with a myth that started becoming very popular in the 1990s. The internet was invented by the Pentagon and designed to survive a nuclear attack. This was a standard narrative, partly because of ARPANET being partly funded by the Department of Defense in the US, but actually it wasn't a contract to create something like this. That was not at all how it happened. Truth, whatever role you wish to attribute to ARPANET as regards the origins of the internet, it is clear the early internet was not motivated by considerations of nuclear war. The decentralized structure actually came from a very different set of considerations. A need for technical protocols to allow computers and the users to communicate. It's primarily an early computing science exercise rather than a military one. It's to allow people to try and connect and communicate and not have to trust any form of centralization or for that to exist. It was done between universities and related sites in the US. The point there is there is no center, and that's the distributor. If that happens to survive a nuclear attack, well, that's a nice side effect, but that was not a design intention. So that's one of the myths. So let's talk about fallacies. And there are these things these fallacies, a list of, well, we'll go through the numbers in a moment, that became famous, originated at Sun. L. Peter Deutsch first created a list of 7 fallacies in 1994.
I really hope that's not true. Because then it's a fallacy.
Meta. Oh no, sorry, that's a TM now. I can't say that, can I? Bill Joy, famous and cursed for the invention of VI in equal measure. So this is the original kind of Sun crowd, the BSD Unix kind of crowd. Dave Lyon already formulated a list of flawed assumptions about distributed computing that were guaranteed to cause problems down the road. The network is reliable. So if you're in the UK, in the lead up to Christmas 2018, this was kind of interesting. There's a very high chance that if you were using the O2 network, you weren't using the O2 network. It was a fairly major outage. 30 million customers unable to get online. This is fairly major. You just can't trust the network. And sometimes people think of the network as being something abstract and internet-y and hidden from them, but honestly, just pick up your phone. You know, this is all network. Second, latency is 0. Yeah. You ever had this problem? You go to something, you open it up. It could be on your phone. It could be on the web. You go to something, and it's got your stuff. I don't know what your stuff is. It could be your money. It could be your prized possessions. It could be your orders. And you go to it, and it says you've got nothing. And then your heart skips a moment, and then it says, oh, actually, here's all your stuff. This is because whoever wrote that assumed that transport is instantaneous. There is no latency. That what you've got is you've got a collection of stuff. What's the initial state of a collection? Empty. Right. And that's fine if you're dealing with a nanosecond response. Just for clarity, a nanosecond, a light nanosecond, is the distance across my laptop, which you can't see. A light nanosecond, so a convenient measure, is a pad of A4, which I have somewhere. No, apparently I don't. Yes, I do. 2 pads of A5, that makes up an A4. So there you go. Across the top there, that is a light nanosecond. Because you see, light sounded really fast earlier on in the talk. 299,792,458 meters per second. Wow, that is fast. It takes 1 nanosecond to go from my right hand to the left hand. That gives you a cycle time of the order of gigahertz. That's not very fast at all. By the time you're hitting proper scales, this is hideously slow. So you end up with these unwanted effects. And is that the fault of the speed of light? No, because the speed of light was given. That's a fault, as John Carmack observed, a large fraction of the flaws in software development are due to programmers not fully understanding that all the possible states their code may execute in. In this particular case, The problem we have is that somebody has decided that they've got a collection of orders, and its length is it's gone into a displayable state initially, and we're going to show that. And then we received the loaded event, and at that point, orders of length 3, we now have populated this, and we do a refresh. This is not the correct way to write this. Well, I mean, I'm going to use the word correct like it's a really strongly defined thing. So sometimes correctness is a mathematical thing. Sometimes correctness is a much softer social thing, pissing off your users or surprising them in unexpected ways. If you're doing that, I'm going to call that incorrect. We can debate that later, but I'm happy to call that incorrect. So the way you want to do this is to recognize you have a state model. If you are doing UI work and you're not comfortable thinking in states, this is an opportunity for improvement. This is, I think, the first time I was ever taught state model. I'm not saying you need to draw diagrams, but it certainly helps. The first time I was ever introduced to state modeling was actually in the context of UIs. It's just like, oh, you're in this state, then you're in this state. At this point, we know something. You don't have this information. This is like the whole happened before thing. You don't have this information, so you cannot display this. We get this frequently. You know this experience, that notion of, you need to put in correct data in this field. So what do? You flip round to another screen to copy and paste it off something else, and you get back to this, and it says invalid data because it decided to perform a validation. It's not invalid data. There is no data. It has not, somebody has incorrectly modeled the empty state as invalid. It's not invalid. It's, wait a minute, I'm a human being. I'm going to get something, yeah? Do not judge me, machine, for I will throw you out the window. I've seen the Terminator films. So, the point here is I know what's going to happen. But this is what we're doing. We're modeling this. There's nothing there, so there's nothing to display at this point. Then we receive the loaded event. Now it's displayable. We've moved to that. It's a very simple idea. And none of this would be relevant if that all happened within a nanosecond, if it were all local. But we care about this. This is what you want. Yeah? That's the right way to do this. We don't have the information. It's not zero, it's just not known. It's to do with knowability. We actually don't know the answer at this point. So I'm not going to tell you that we do. I'm not going to fake it up as 0 or something. So the other one, bandwidth is infinite. It's not just the speed of light that we need to worry about. Bandwidth, there is a finiteness to this. So nothing in nature is truly infinite. Okay? Infinity is not a natural thing. Okay? It's a mathematical construct. It's made up by mathematicians. When a physicist tells you that something is infinite, it's a polite way of saying our theory does not work at this point. But rather, it's the way that software people don't use the term infinity. They just say it's unbounded. Yeah, it's going to crash at some point, but we don't want to look at that. Yeah, software does that. Physicists say it's infinity because to say our theory doesn't work doesn't sound quite as cool. The only way that infinity exists in the universe is because humans create it. So I live in Bristol. This is from the Bristol Beer Factory. There, infinity. See, human construct. So. Network is secure. Yeah, that's not a thing. So back to this. James Gosling had actually codified these 4, calling them the fallacies of network computing. Deutsch wrote the list, by this time 7 items strong into a slide presentation. So I think we're around 97 at this point. Topology doesn't change. Yeah, things move around all the time, and this is before we hit mobile computing. There is one administrator. Transport cost is 0. This is interesting because this one's ambiguous because sometimes people sort of talk about this as being the cost of marshalling and unmarshalling. At other times, people actually talk about it as cost. Nothing is for free. Gosling added the 8th fallacy in 97 or so. So it's normally seen as the 8 fallacies. The network is homogeneous. Yeah, that seems really familiar. Let me go back to 1989. Oh, yeah, there we go. Yeah? Honestly, we should get out and talk a lot more because there was 8 years between these 2 moments. And that's the point. I kept wondering, it was really interesting in the 2000s when people say, oh, Kevlin, you come across the fallacies of distributed computing. I said, yeah, but everybody knows this. I was wrong. They didn't. Because that's a really good example of local versus remote. There was not global consistency. I knew something, but it turns out not other people didn't, simply because I was taught in a particular way. Yeah, that was just luck. It wasn't anything clever on my part. Okay. In an episode of Software Engineering Radio, Peter Deutsch added a 9th fallacy. I'd just like to say that if you Google around the internet, you will find other people have added their own addendums. mostly they're wrong, irrelevant, or they just don't fit with the previous 8. They are, but Deutsch gets a special. He gets special consideration, given that he kind of wrote it. So I'm going to give him a get out on this. It's really an expansion of number 4. It extends beyond the boundaries of the physical network. The party you're communicating with is trustworthy. Friday the 13th last year. Everybody's going like, but surely, Kevlin, you mean Friday the 19th? You're developers, think in hex. Yeah? 13th, good. CrowdStrike. It was a very busy day. I got a lot of ats. This is interesting because it also highlights something else. This is a major security incident. And how do we know it was a major security incident? Because the CEO of CrowdStrike said it wasn't. That's how you know. Turns out a failure is equivalent, is from the point of view of any usage, is almost equivalent. Any kind of defect is equivalent to a security attack vector. Okay, there is no difference from most people's point of view. They're normally the same door. But what is interesting here, and let's go back to that O2 outage, was caused by an expired certificate and could easily have been avoided. I think it's interesting. I think Jimmy mentioned the expired certificate problem earlier, and this is the point. That was a fairly major thing, an expired certificate. The point here is that when we say not trustworthy, the immediate default in your head is somebody who's being malicious. Guess what? There's various wordings for Hanlon's razor, but this is one of the more polite ones. Never attribute to malice that which is adequately explained by incompetence. It turns out that most of the issues that you need to deal with when we talk about trust is not to do with malice. It's not to do with Machiavelli, it's to do with Murphy. It is just, it's a case of like, yeah, actually, things go wrong. People screw up. People forget things. People don't get things right, and that's it. It's actually not people being mean and nasty and all the rest of it. They certainly exist, but actually the greater class of untrustworthiness has a far simpler and less malicious explanation. So let's hit 1994. What I find interesting is that this is at Sun Microsystems, and there seems to be no reference or relation to any of the fallacies that were drawn up by L. Peter Deutsch. Again, folks, it's good to talk, especially if you're in the same organization. So this is 1994. I think the main, so this is Jim Waller, Jeff Wyatt, Ann Walrath, and Sam Kendall. I think the main contribution criteria for this paper is your surname had to begin with W. It's an unusual grouping statistically of last names, but a couple of points here they made. There are fundamental differences between the interactions of distributed objects and the interactions of non-distributed objects. Distributed object-oriented systems based on a model that ignores or denies these differences is doomed to failure. And what is interesting from this point of view is they then go on to pretty much say everything that the answer paper said. What I also find interesting is going back to the answer paper, I reread some of the stuff recently, is that they were actually talking about an object-oriented model for the network in the late 80s. And actually, if you look at some of the DCE RPC stuff, they were talking about it as well. So they were talking about it from that point of view. And that's long before this stuff went mainstream. So there's this kind of repetition here. We then saw this observation that was made. So Jim Waldo was one of the people responsible. If you've worked in Java RMI was kind of, he was involved in that. And very much an RPC-based model. And actually a slightly annoying RPC model, as it turned out, because there was the idea that distribution is not a transparent thing, so we're going to make sure you know that you're touching the network. We're not going to pretend it's not there because it has these failure modes that are unusual, so we can't make it completely transparent. It's kind of like we like the transparency idea. This call it can either happen locally or it can happen remotely. And it's a very attractive idea. It means I don't have to write 2 sets of code. If I am doing stuff locally, I write this code. Else I do stuff remotely and I write all of this code. We would like to take that out of our application. And polymorphism and various other constructs allow us to do that. The danger with that is that sometimes you hide the thing that you're trying to hide. Which, well, why is that a bad thing? Well, you don't know you're doing it. One of my clients had exactly this problem. It's just like, yeah, we're now doing this, and our application runs really slowly. And you looked at the code, and it all looked really simple, except that every single call was a tiny, tiny call, like getter-level call. It just happened to be going out on the network. It's kind of a very chatty protocol because you couldn't see it from the domain code. It's just like, the conversation with the database that goes something like this. Hey, you got anything for me? Yes. What? 5 things. Could you tell me the first one? Yeah, here's the first one. Could you tell me the second? This takes time. Yeah? It's kind of rather than what you expect in something that responds to the fact that the landscape, the timescape, as it were, looks different. What you do is you say, hey, send me everything you got. I'll figure it out. In other words, that's a single round trip. And that transparency, the problem is that when we write the stuff from a normal point of view, for loops, iterators, all the rest of it, it all seems very, very simple. You're just going around the loop, you're doing something once, it's nice and easy. But then you add a piece of wire in between that, and suddenly you incur a cost. Okay? I mean, it's if I decided the nearest supermarket from my house is 5 minutes walk away. I go to the fridge, I see we don't have milk. I go to the supermarket, I walk in, I get milk, I buy it, I go home, I put it in the fridge. We're out of apple juice. I go out the house, I walk to the supermarket, I go get some apple juice, pay for it, go back home, and do that. This is going to get your steps in. That's a plus. But each round trip is huge. You're also going to get the whole trustworthy issue as you start walking to the supermarket. You get the staff there going like, watch, he'll be back in 10 minutes, and you'll buy one thing. But the point there is what you do is you execute multiple loops in different contexts. Okay, let's go around the kitchen, see what I need. Shopping list. Right, first collection, first set of iterations. You go to the supermarket, you iterate around that, you marshal once into the bag, get back home, unpack it. There's a lot of loops there, but there's only one round trip cost. The point here is that transparency has these two sides. So the problem is that a lot of people, when they started going, hey, objects, perfect for distribution, did not work very well. In fact, it worked very slowly. To the point I met an architect once who said the observation, I don't like it when I give my developers the design. You can tell what era this was. Actually, in some organizations, this was probably last week. He said, I don't like it. And I said, well, why not? Well, they take my designs, and he said it with distaste. They make them work. It was like that was a bad thing. Because what they did is they made them implementable, because they looked at that and go, well, this is ridiculous. You just go to the supermarket lots. This is not practical. Oh, you need to make this a much more batch-oriented interface. You need to do this, that, and the other. You haven't accounted for the failure modes. And the architects go, la, la, la. I like them. It looked good on the whiteboard. That's good enough for me. So the problem here is you can't just take stuff that worked locally and just throw it out. The problem is that we're normally taught this stuff locally, and it appears that way. We have the frameworks that mask this and support that illusion. The problem is the physical illusion doesn't follow. We end up with exciting failure modes and huge latency. So Martin Fowler's first law of distributed object design, don't distribute your objects. There we go, that was easy. Talk over. Okay, but now you are distributing stuff. Whether they are classic objects or not, it's not the point. If you find yourself in that position, then you have to appreciate other physical aspects. So let's talk about what was originally called by Eric Brewer, the CAT principle. He introduced this in 1999. Then he upgraded it in 2000 to being a conjecture. And then it was actually proven in 2002. It's a proper theorem. It's not just somebody throwing the word theorem around. Somebody actually went and proved it. Seth Gilbert and Nancy Lynch. Brewer's conjecture, so it was known as Brewer's principle, conjecture, theorem, etc., and the feasibility of consistent, available, partition-tolerant web services. When designing distributed web services, so again, everybody anchors to whatever was going on. You can tell 10 years earlier, it's all about the objects, and here we are, it's all about the web services. There are 3 properties that are commonly desired: consistency, availability, and partition tolerance. It is impossible to achieve all 3. CAT theorem is what's known as an impossibility theorem. In other words, here's the thing that is actually not possible to know. It's not a proof of something, it's a proof of not something, if you like. So let's look at those 3 terms in a bit more detail. When we say consistency, it is the idea that if we are in a network, there is a data item, and we have two observers, two clients, and they both request the value for that they have the same view. Okay? This could be as simple as the two of us are standing side by side with our phones, and we're on a social network. We do an update, and we see, oh, did you see that thing that Fu just posted? And you go, yeah, and it's the same. That's all we're saying. There's nothing fancier than that. But we can dress it up in database language if it makes you feel more technical and comfortable. But that's the point. That's all we're doing. It's consistent. We see the same thing. Or, if we're not in a position to do that, then one of us gets an error. In other words, I'm either going to give you the right answer or, I'm sorry, this is not available at the moment. Availability is the idea that an answer is always available, even if it's wrong, okay, or not up to date. This is where caching fits in. Okay, it's the idea of, yeah, I've got an answer, but actually, it turned out that Fu posted something slightly different, and you haven't got that. Oh, you must be, you're taking a different route through the network. Okay, so the point here is that an answer is always available, but it might not be the answer. Partition tolerance deserves a little bit of explanation because the other two are intuitive. Partition tolerance, I mean, honestly, I wish you'd just call it tolerance, because that would have given us cat theorem. And everybody knows the internet is about looking at cats. That would have been way funnier, much deeper, and the source of, more people would remember it for a start. It would also allow me to play with quantum mechanics jokes a lot more. It's a missed opportunity. I don't have a time machine, we can't fix it, so let's talk about what it is. Partition tolerance, if you've got a network of nodes, everybody can kind of communicate one way or another with everybody else. Now, that's a network. If we take out this node, this part goes dark. What we have effectively done is this is a network partition. Effectively, we have two networks. Yeah? But the point is it doesn't have to be a bit of the network. This is equivalent to saying that a server has crashed, not just a router. So, a partition, fancy way of looking at it. Alternatively, we can just say it's a network. If you speak Russian, it's a network. There's a lot of ways we can play this. But the idea is that it's not that you cannot have all three at the same time, it's that you cannot guarantee all three at the same time. If a system is constantly failing, then you have another problem. But it's the idea, most of the time, most of the stuff is, that's fine. So you have C, A, and P, it's just you can't guarantee. Sometimes people misinterpret the CAP theorem as saying you can only ever have two of these. It's no. Is you can only ever guarantee two of these. You might have three at certain points, but you cannot guarantee. There's a very subtle distinction. But what we can say is we can have consistency and we can have partition tolerance. In other words, we continue running. This is how we deal with partial failure. Client's running, server is running, boom, and then there's an outage. Okay, in what way are we tolerant? Well, I haven't crashed. Perhaps the server hasn't crashed, it's just routers in between us. Consistent, can I get the latest values? Maybe that server is serving somebody else. No, I can't get the latest values. This is where I'm getting this isn't working for us right now. But I don't get any other values. Whereas in this model, I do get the last best value, for example, the last thing that was cached. I'm always getting a value, but I can't guarantee it's the most recent. Okay? And then we have this limiting case. And when I say limiting case, some people say, oh, well, that's not a very useful case. Because here, I'm absolutely getting the latest value, and it is always right and all the rest of it, but we cannot tolerate any network partition. This is actually the limiting case for single process application. In that case, you don't need to worry about that. But the idea is that you can only ever guarantee. So sometimes a system will be designed to accommodate and bias towards one or another. Sometimes it emerges out of the properties of the system. It's not somebody on the server, it's maybe how people configure the clients. The deeper aspect of this is that what we find in this, as observed by Douglas Adams in The Hitchhiker's Guide to the Galaxy, is we demand rigidly defined areas of doubt and uncertainty. That is what the CAP theorem is. I cannot guarantee all of these properties. In this sense, it is a bit like Heisenberg's uncertainty principle. It's just like we have a limit on what we can absolutely guarantee and know. It's a boundary of knowability. Now, into this, what we see is that sometimes you get stuff like this as well. Oh, by the way, that's all eventual consistency stuff. This is a problem. You've undoubtedly encountered this. Occasionally I encounter this on applications which tell me, hey, you have 7 things, and actually you look at the list and you're showing me 8 or 6. It's a different number. It's not the right number. And I've had people say, oh, yeah, that's eventual consistency because the values come via different paths on the network. This has nothing to do with eventual consistency. There's a name for this. It's called a bug. I mean, literally, you are on the same screen, and you have a collection of 3 things, and you are calling it 2. I don't care of the provenance of 2. You just listed 3 things. Use the bloody container size. That's the right answer, okay? So I made this mildly frustrating. I obviously had a bad day when this happened. It is a feature of a distributed system that it may or may not be in a consistent state, but it is a bug for a client to contradict itself. So the point here, and you get this is encouraged, unfortunately, by stuff like micro front ends and things like that, where people then use it as an excuse, as a crutch. It's like, yeah, the data comes for who knows. It's all a bit woo, and it's not magical. There is nothing magical about this, except the magical thinking that goes into saying this is okay. You are in the same process. At that point, it is your job to reconcile your version of reality and present it to the user. This is user interface design, just as the state modeling is user interface design. Okay, what is the experience that we're getting? Are you confusing the user? If so, well done. So the point here, we'll take this a little bit further. This is the PACELC theorem, because you can never let a good theorem die. So you take the 3 letters of CAP and flip them around, and you got the first 3 letters here. So this was Daniel Abadi in 2010. It was proven to be a theorem in 2018. And it is partly a response to the idea that people got a little bit fixated on the idea that you can only ever have 2 of the properties. And he said that's not what this is describing. But that people kind of stop with the idea you can only ever guarantee 2. He said there's a little bit more to it than this. So the way this breaks down is that partitioning is a question. Are we partitioned? Because as I said, most of the time things are up and running. So for any given client-server relationship, we find that actually we're probably not crashed at this point. So are we partitioned? If we are, then we have to make a design choice, or rather, we can, at this point, only guarantee one of the other 2 things. If we wish to be tolerant of partitions, in other words, for everybody to continue running in some way or another, even if it's not that useful, we have to choose, what do we favor? Am I going to give you the most recent value, or rather, are you going to receive, because it might not be me, the server, are you going to receive, is it by design? Because remember, a system, we use the term system these days, people freely use the term system for sometimes what we call a program, and I want to make a slight distinction, is a system is many of these programs bound together, and that's the point, is that it's a cooperating system. So the idea is, do we favor what are we going to try and guarantee in this context? In the presence of network partition, do we favor availability or consistency? Otherwise, we have a choice. It's all good. We have a choice here between and this is slightly reversed. Whenever anybody talks about latency, do make sure you pick up the right sense, because we're not encouraging latency, we're trying to reduce it. Latency means no latency, or minimal latency here, yeah? So the idea is, what are we trying to reduce? Latency, or are we trying to maximize consistency? Okay, the idea is if everything's working, we have a choice. I can either make this super fast or super right. That's your choice. So that, again, the caching thing comes in, because that's often, if you're going to introduce a cache, it's going to minimize latency, but it might give you inconsistency. It's a conscious choice. I'm not saying there's a right or a wrong answer. I'm just saying you only get to choose one of those. Yeah, I have had this conversation with a team when I remember sort of saying, they sort of said, okay, we have to do this, we're trying to do this, and this is about 10 years ago, and they said, I didn't know the existence of this theorem at that point, but I did sort of say, I think there's a problem with what you're asking. They said, no, but the product owner has asked for this. Yes, and the architect has sort of said that this other thing is a key property. I said, that's not possible. Oh, but we have to do it. And I said, no, I don't think, when I say that's not possible, I'm talking laws of physics not possible. I'm saying mathematically impossible. You are asking for something that is impossibility. And they kind of looked at me blankly. Yeah, but we have to do it. It's just like, it's one of those things where you've just told something that's broken their world and they don't know how to respond. I said, you cannot have these. And we sketched it out on the whiteboard. I said, these two things cannot simultaneously be done. Had I known about the PACELC theorem at that point, I would have been able to say, aha, I see what you're trying to do. No, you can't. You're trying to maximize. You're trying to have minimal latency and maximum consistency possible. That is not possible. You don't have that choice. You can trade one off against the other, but you can't have both in the way that you want them. And basically, you get a number of configurations. In this configuration, what we say is, OK, so this one's a performance-centric view. We are always giving the answer. It might not be consistent, but we are always giving the answer. In the presence of network partition, I'm going to give you an answer. Without network partition, I'm going to give you an answer as fast as possible. Okay? Alternatively, we might say, in this particular case, I'm going to give you an answer, but all other things considered equal, I will try and make sure it's as right as possible. Okay? This one's a slightly odd one, because this one basically says, I'm going to totally value that you get the right answer if it's available. Otherwise, I'm going to be super fast. That feels a little contradictory, but we don't want to eliminate that as a possibility because everybody loves a quadrant diagram. It's the weirdest quadrant of the lot. And this one basically says, yeah, always favor consistency. We're always going to try and be as right as possible, no matter what the cost or whatever. So, and this is quite a useful framework. Again, this is, you're not choosing to follow CAP or PACELC or anything like that. You are choosing, you are understanding that this is the way the landscape is, these are my choices. That's what you're doing in this case. Okay, so let's just wrap up with something slightly different, a slightly different perspective, to bring it back to the physics of this. Back to our friend C, which is indeed a constant, except, remember I made the qualification earlier on, by default when somebody says, oh, it's the speed of light, they are normally ignoring the annoyance of media. And I don't mean that in the social media sense or the newspaper or TV media, although those are super annoying. I mean this in the sense of the fact that there is a thing called refraction. Currently, I'm experiencing refraction because I'm wearing contact lenses. Given the general sightedness of those people involved in software development, I'm looking around the room, and I can see a number of pairs of glasses, and I'm imagining that half the rest of you have contact lenses. So the point is, we all experience refraction on a day-to-day basis, and that is what happens when light goes through a different medium. So substances have refractive index. This is known as N, for those of you who can remember your physics, and it is basically to do with the difference of the speed of light in two different media. That, in this particular case, my contact lens and air. And that's the difference. When it crosses, there is a difference in the speed of light. And that causes really exciting effects like this. Probably the best demonstration of this is to be found on Pink Floyd's, well, there's a debate. We could start an argument now about which is the most classic album. Those in favor of Dark Side? Those in favor of Wish You Were Here? Yeah, okay. I'm sure there's a few Wall fans out there, but, you know. It's not that good. I'm more of a Wish You Were Here kind of fan, but Dark Side, classic album. There's only one small issue, is that actually, it would look like this. Somebody actually did the experiment. Turns out glass has a far higher refractive index. Light is a lot slower in glass than suggested here. This would be kind of quite light. It would be like a thick gas. But this is the reality of it. So here's the interesting thought. You can actually treat, so there's a bunch of stuff here that we want to clear up. Speed of transmission in air is c, and in a wire it's close enough to c. I mean, in air I'm saying it's close. In a wire, the thing to keep in mind, it's nothing to do with electron velocity. It's an easy thing to assume it's the electrons moving, that it's the speed of that. No, electron movement is important, but the speed is not. It's the wave. The wave, just as if you watch a water molecule in the ocean, it will, and you can see the waves rolling into the shore. They're not rolling into the shore. Those molecules are mostly staying where they are. They're normally following an elliptical path. Okay? The overall wave is carried. It's the speed of the wave, not the particles in the wave, that matters. And so basically, in a wire, it's about 90. It's about 100. We can call it C. The slowest medium any message travels through is software. I want you to think about software as being something that has physical properties. What is the job of software? The job of software is to slow the hardware down. Hardware is fast. Software is there to just say steady on. I'm sorry, we don't drive that speed around here. Some of the speed loss is necessary, of course, but much is not. Most software is wasteful of its resources, including time. This means we can reconsider networks and software systems as pieces of running code as having a refractive index, which is more likely variable. But the idea of your software has a refractive index is quite a cool way of doing it, because it's a measure of how much it distorts or reduces the speed that naturally a piece of hardware could go. So if we've got something like a network, and we've got 2 points on a network, this is not the direct line. Okay, let's be very clear. This is the most direct route. Okay, so that is the fastest you can travel. Of course, routers can do other things and craziness. This is where we start getting a bit of weirdness. We're getting a slowdown at this point, and that decision was made by pieces of software. But let's actually put some nodes in that have cost. These can be routers, these can be our systems. Okay, now, when we go across the network, it's going to be slower than it was, in the first diagram. And we can actually measure this. We can say, what's the ideal velocity versus the actual? And that gives us the refractive index. In fact, you don't have to measure the velocity. I'm not asking you to go out and measure the velocity. You can actually just do it with time and just measure the ends. And how long did it take? How long would be the ideal time? And that's the refractive index. And I bet it comes off a lot worse than the whole Pink Floyd thing. Okay? And if you want to factor it differently, you end up with this. Overhead. There is an overhead cost. Some people like to replace the word overhead with software. Normally they come from the accounts department, but in this particular case, we can actually look at it from a different perspective. This goes back to that idea. So the job of software is to slow down the hardware. Yeah? So, on that, and what looks to be dangerously close to actually being the right finishing time for once for me, the concept of time is fundamental to our way of thinking. And this is important. What Lamport is saying, Leslie Lamport is pointing out, is that our view of time misinforms our personal view and also our programmatic view. Misinforms us as to what's actually going on. You have this very privileged perspective through the window of your IDE that makes it distributed systems are somebody else's problem. A distributed system is something to do with a piece of software that we are using as a company. It's a bit of middleware that gets loaded into the stack, and it's just a box on the stack when we draw it from the top of the screen to the bottom of the screen, or the top of the whiteboard to the bottom of the whiteboard. And we think of it like that. I want you to think about it as actually being something quite different. It introduces a fundamentally different set of assumptions and breaks the kind of naive physics that we often have about our code, and it's worth being aware of it. So I will close with Douglas Adams' observation that time is an illusion and lunchtime doubly so. It would be better if this were a lunchtime talk, but honestly, I can't rearrange the words of the great man. Thank you very much. On that note, I'm happy to answer any questions come up and chat, but I'm also around tomorrow.